Welcome everybody to Harmonic Analysis Seminar. It's our great pleasure to have March Boedihardjo from UC Irvine, who is going to talk about estimating average of function on Boolean cube without risk. Please, Mark.
All right. Thank you for the invitation. Yeah, so that's what I'm going to talk about today. Certainly not estimating all function, but some functions on Boolean cube without risk on accuracy, but there could still be risk on complexity. Okay, I will talk about that. All right, so just want to explain the context. Suppose we have the function from the discrete Boolean cube consisting of 2 to the power n points to R. So n is going to be large, maybe 100, let's say. So that's the average, sum up all the values of f and then divided by 2 to the power n. Okay, so if we want to compute this directly, that's going to take exponential time in n. But of course, the result must be accurate. If we're willing to take some risk, then we can take some samples and then compute the average of f over these samples. And in this case, this will give polynomial time computation, but with the trade-off of being some risk there. What's the risk? The risk is that there's still some little chance, little probability that these two are far away. Okay. So if we're willing to take some risk, then we can do it in the polynomial time. Okay. So the problem is whether we can achieve polynomial time, but without taking any risk on the accuracy. So that's the problem. So, I mean, so to be more precise, so this is what I want to obtain. So let's say I want to obtain a theorem that the average is going to be within, let's say, 0.1 from 1.5, let's say. So establish a theorem. So if we take some samples and then we take the average over these samples, we're only, let's say, 99% confident that some statement like this is true, but it's not that we know for sure it is true. So what do I mean? So this is a theorem. What's not a theorem if I say, well, I'm 99% confident that Riemann hypothesis is true. Now, this is not a theorem, okay? So what I want is to establish a theorem, not some statement about confidence, okay? Something that yes or no whether it is true. So that's the goal. But I want to achieve this thing in polynomial time. So that's the main difficulty. Okay, so here's the strategy that I propose to solve this type of problem. So two-step approach. Well, the first step is just what we usually do when we take some samples and then we take average over these samples. As usual, we know with high probability this is going to be true. But we put a second step, a certification step, to certify this. What do I mean by certify? So certify that they're good samples. What are good samples? Good samples means that these two are close. Okay. So we know, of course, that with high probability, these two are close. So the event that these two are close is going to have high probability. That event has high probability. But certifying that these samples are in that event, that's another story, okay? With high probability, well, they lie in that big event with very high probability, but certifying that it is in that event is, it's much more difficult because that event, it's like we're putting the problem to we're just hiding the problem. We're not really solving the problem, it looks like. But so certainly the first step is the easy part. The second step is definitely the hard part. I mean, we're just hiding the difficulty in the second step. You can say that. But anyway, this is the strategy that we're going to use in the rest of this talk. So yeah, so first step is the classical step. The second step is certification, and I'll talk more about the second step later. How do we certify that the samples are good samples? To certify that these two are indeed close, rigorously certifying. So rigorously showing that these two are close. Okay, so this is the easy step. This is the more difficult step. All right. So it might seem that it's not possible, but in another context, randomized quicksort, so the problem of sorting a list of numbers, in another context is the reverse. Certifying is the easy step, and running the algorithm is the harder part of the problem, because certifying that, let's say this is my results, that's the ascending ordered list. Certifying is easy because you just have to show that this is less than the next one, the second one is less than the third one, and so on. So you only need to check n-1 time. So certifying is easy. Running the algorithm is the harder part. I just want to bring up this randomized quicksort so that you will have a better idea of what I'm trying to do. So for the randomized quicksort, the result must be accurate. Why is the result must be accurate? Because if it is not in ascending order, then we keep on running the algorithm until it is in ascending order. So it must be accurate. The only issue is that we might keep on running the algorithm indefinitely, and that's the only problem. So there's still some tiny chance that we can run the algorithm forever. But anyway, the expected complexity, so with high probability, the complexity is going to be in polynomial time. So yes, so there is still some risk, not the risk on the accuracy. By accuracy, I mean we produce a result that is not in ascending order. So there's no risk on the accuracy. There's only risk on the complexity. It might take forever to run the algorithm, but that's only with tiny chance. Okay? So in other words, we're just moving the issue about the risk from the accuracy to complexity. So that's what randomized quicksort does. So no issue on accuracy, only some risk on the complexity. So there's still some tiny chance the complexity could be high, but expected complexity is polynomial time. All right, so let's go back to the strategy that I proposed for estimating the expected value, or the average of the function on a Boolean cube. So the first step, as I said, is pick a set of samples and then take the average on these samples. Okay. Suppose we can actually certify these samples that they're good samples. It will make these two small. The difference is small, these two close. If we can certify that they are good samples, by certify, I mean we can rigorously show that it's a good sample, these two are close. If we can rigorously show that these two are close, then okay, we are done, because then we can rigorously show that these two are close, and thus we obtain a rigorous estimation for the average of F. Okay, if we fail to certify, then take another set of samples and then do this again. And then for the other set of samples, can we certify? If yes, then okay, then we get accurate estimation, a rigorous accurate estimation. If not, then take another sample, keep on going. But if we know...
Can I ask a question?
Yes.
Do you pick samples from the uniform distribution?
Yes, uniformly, IID uniformly from the Boolean cube, yes.
And okay, and another question, do you put any assumptions on f, or f is an arbitrary function?
So in this setting here, f is arbitrary, but later I will impose some assumptions on f.
Okay.
Obviously,
Okay,
it's not going to be possible to do certification for
cool. You're
arbitrary
right.
function. But at least for certain type of function, if we're able to do this certification process, then we can keep on running until we get a good set of samples. And if with high probability that a random sample is good sample, then it's even likely that the first trial, the first time we take a sample is already successful. Okay? So then with expected complexity, it's going to be in polynomial time, and then the result must be accurate, because if we cannot certify, then we take another set of samples. Okay. All right, so I mean, certification of samples, that's definitely impossible for arbitrary function, because, well, for this set of samples, f takes these values, but then it won't tell us anything about what's the value of f for the other inputs. Okay, so it's impossible to certify for arbitrary function, but maybe for a certain class of functions, certification is something possible. So that's the problem. And in this talk, I will identify a class of function where such a certification procedure is possible. That's what I'm going to do. Maybe beyond what I do in this talk, there might be other examples, I don't know. But today I will identify a class of function where this is certification process is possible. Okay, so that's the class of function. Okay, before that, suppose we have a function from the Boolean cube to the real line. We can always write that in Fourier expansion. So AS are the Fourier coefficients. So we are summing up over all the subsets of 1 to n, AS, and then the product of this epsilon k. Okay, so, you know, because these products of epsilon k's over a subset of 1 to n, that's an orthonormal basis for the space of all functions from this to this. So every function can be written as this, in this form, and then the AS are the Fourier coefficients. And note that the average of f is just A of the empty set. We're summing up overall the set. For the empty set, A of empty set, that coefficient, that's the expected value of f. Okay. So the class of function that I want to say is this. Assume that all the Fourier coefficients are non-negative. Okay, so that's the class of function. Okay, so first we are able to obtain an upper estimate for the expected value of f. So that's an upper estimate. Okay, not a perfect estimate, just an upper estimate. So we just take some samples, x1i to xni. Okay, this is going to be true. Okay, this is a non-random statement. It's not that this is true in expectation on the right-hand side. No, this is always true for all choices. Okay, regardless of whether we pick them randomly or not. This is a deterministic statement. Okay, the proof is pretty easy because we are assuming that all the Fourier coefficients are non-negative. So for this one, if we just plug this in, this function, we write the function in this form, just put this here. We just get this one, okay? And then you can see that you can write this in a square form, like this, okay? And then, so every term here is going to be non-negative. Every term is non-negative, and so it's greater than equal to the term where we have S equal to the empty set. If S is empty set, if S is empty, we are just summing over something empty, so that's just 1. So if S is empty, this is just 1, and the average of 1 is still 1. 1 squared is 1. So S is empty set. This will give us A of empty set. The rest are all non-negative, so this is greater than or equal to this. Okay, and A of empty set, that's the expected value of F. Okay, so this gives us a upper bound for upper estimates for the expectation of F. So is this a good upper estimate? Because this is going to be true for all x1i to xni, regardless of whether we pick them randomly. Well, it is going to be a good estimate if p is large enough, and if we pick these x1i to xni randomly. So if we take the so this is always true, okay? This is a non-random statement. But with high probability, this is going to be a tight estimate, because if we take expectation on the right-hand side, this is going to give us this thing. Why is this true? Because, well, we just split this sum, okay? Split into I equal to j and split into I not equal to j. If I is equal to j, then x1i times x1i, that's equal to 1, because everything is plus or minus 1. Okay, x1i to xni are all plus or minus 1. So if I is equal to j, then everything is 1. Okay, and there are p of them, and then p over p squared is 1 over p. And then if we sum over I not equal to j, and if we pick these x1i to xni uniformly and independently from the Boolean cube, then these are still IID Bernoulli random variables. And if we take expectation with I not equal to j, that just gives us the expectation of f. Okay. So if p is large enough, and if f of 1111 is not too large, yeah, that's the hidden assumption. F of 111 is not too large. That's the hidden assumption. If p is large enough, this is approximately E of f. Okay. So yeah, so for the upper estimate, this is always true, and with high probability, this is going to give us a tight upper estimate. Okay. Yeah, so we can keep on taking some samples. Let's say we do this, 1,000 times, and then take the minimum of all these. Okay, we can take 1,000 sets of samples and then do this procedure 1,000 times, and then we just take the minimum of all the 1,000 times that we did, and then it's still going to be at least the E of f, and with very high probability, it's going to be close to EF. Now, there's still some issue here, because this is only an upper estimate. Okay. We just know that it's going to give us an upper estimate, and this upper estimate is going to be tight upper estimate with high probability. But we are still not able to certify that this is a tight upper estimate. So we can certify that it's an upper estimate, but we cannot certify that it is a tight upper estimate. That's the problem. So we still haven't solved the problem. We only solved half the problem, because we're only able to find an upper estimate. We cannot certify that it is a high upper estimate. We can only certify its upper estimate, but we cannot certify its high upper estimate. But we do know, however, that with high probability, it's going to be a tight upper estimate. But we cannot certify that it is a tight upper estimate up to this point. Okay? So we haven't solved the problem. What's remaining is certifying that the right-hand side is actually a tight upper estimate. So yeah, so we still haven't solved the problem. Okay, so how do we certify that the right-hand side is a tight upper estimate? We know for sure it's upper estimate, but how to certify that it is a tight upper estimate? Okay, so that's the strategy. Use the comparison test, some kind of comparison test to certify that it is a tight upper estimate. Okay, so comparison test, that means we use another function to certify this function. Okay, so imagine that we're able to find another function that will help us certify this function. Okay, the other function will satisfy this property. All the Fourier coefficients of that function are at least the Fourier coefficients of f, okay? As are the Fourier coefficients of f. So let's imagine that we can have another function and all the Fourier coefficients bound the Fourier coefficients of f. Try to use this to certify the upper estimate for f, expected value of f. Okay. From the previous slide, we know that this is at least 0. This is at least the expectation. But if we can show that this is small, then that's good. If we can show that this is small, then this will give us an estimate for EF. But how do we show that this is small? Well, use this function to certify that this is small. So this is at most this one. Okay, so why is this less than equal to this? Because from the previous slide, we know that this is going to be equal to this. That's how we show that it's not negative. This is equal to this. But we just sum up over all the s non-empty. This is at most this because we just assume that as less than equal to bs. So this is less than equal to this because as less than equal to bs. But this one is just equal to this, okay? Same reasoning, okay? This equal to this, and so this is equal to this, okay? So because of this, so this is less than equal to this. Okay. So if we can certify that this one is small, then we can certify that this one is small. Okay, so how do we certify?
Can I ask one more question?
Yes.
So if you look at the average of f, on the left-hand side, you get 1 over p squared times p times average of f, right? And minus average of f. So it's like 1 over p minus 1 average of f, right? I'm just trying to compare the free coefficients, because in front of free coefficients in this inequality, it seems to me that there is a negative sign, right?
Oh, wait. This one?
Yes, there is minus average of f, and the sum gives you 1 over p times average of f, right?
1 over p times.
There is no, I'm sorry, there is no expectation. Sorry.
Yeah, the expectation of f corresponds to the
Yes, I apologize. Okay, please ignore my question. Okay, thank you.
So if we can certify that this is small, then we can certify this is small. But can we certify this is small? Well, there's a difficulty. How do we certify this is small for a given choice of sample? Well, for a given choice of sample, if we want to certify this is small, well, computing this directly, that's okay, if we can compute the g. But the main difficulty is whether we can compute E of g, okay? That's the main difficulty. If we want to certify this is small, we must be able to compute E of g. If we cannot compute E of g, it's impossible to certify this is small. We need to compute this right-hand side explicitly to compute this right-hand side in order to certify this is small. Okay, so what's a good choice of g? That first, it needs to satisfy this condition. Second, E of g can be computed explicitly. Third, g of any value can be computed easily. So we need to find a g that satisfies these conditions. That would be a good choice of g. And here's a good choice of g. That it's really just sum up all the the gradients, okay? The gradients, the discrete gradients of f at this point.
Laplacian, yes.
Yeah, Laplacian, right? Yeah, Laplacian. So yeah, this is equal to this. This is the cardinality of s, okay? So why is this a good choice? Because AS is always dominated by this, as long as S is non-empty. We only need that this is true for S non-empty, okay? So this is true whenever S is non-empty. E of g is 0, because E of this minus E of this is 0. So yeah, we have an explicit expression for E of G. That's good. This is also computable if, as long as f is computable, if the complexity is just n times the complexity of computing an f. So this is computable. E of G is explicit, it's just 0, and the coefficients dominates the coefficients of f. Okay, so that's a good choice of G. Okay. Yeah, so all right, so that answers the question. So yeah, so that's the conclusion. So here's the algorithm for estimating the expected value of f. Okay, so first the assumption is that all the Fourier coefficients of f are non-negative. That's the assumption. That's the function we use for the comparison test, the g. Okay. All right, so what do? We know this is true for all set of samples, non-random samples. This is going to be true for non-random samples. And I don't put minus EG because that's 0 already. We know this is true, okay? So what's the algorithm, really? So we know this is always true, so what do? We pick these samples randomly. Okay, so first we're gonna estimate for the E of f. This is going to be upper estimate. Okay, so this is always an upper estimate. How do we certify that it's a tight upper estimate? We use the G to certify that it's a tight upper estimate. Okay, so is this going to be small? Well, if this is going to be small, then okay, then we get a rigorous estimation for EF. If this is not small, then pick another set of samples. Keep on doing this procedure until we can find a set of samples that makes this one small. And if we can make this small, then we get a tight estimation for EF. Now, the problem is, of course, is this going to be small with high probability? Well, if we took the expectation of this is equal to this, because why is this equal to this? Because if I is equal to j, then you just get 1, 1, 1, 1. Okay. We get 1 over p times this. If I not equal to j, then we know from before the expectation of g is equal to 0. Expectation of g equal to 0. So for I not equal to j, the expectation is 0. So if p is large enough, it is going to be small in expectation. So with high probability, this is going to be small. So with high probability, this is going to be small. So with high probability, if we take a set of samples, this is going to be small. It's going to be successful. And certifying that it's small is, of course, easy because you can compute this explicitly, okay? You can compute this explicitly, and very likely you're going to get a small answer here. And so very likely we are able to get an estimation for E of f. So that's the conclusion, that's the algorithm really. Keep on taking samples until we get a successful one. Any question before I go on?
Perhaps you still want to make sure that G111 is small, right?
Yes, so that's a problem, yes. So yeah, so there is some hidden assumption here. We need the Fourier coefficients to be non-negative. G of 111 is small, yeah, so we do need that the, yeah, so well, G of 111, that's going to be bounded by n times the L infinity norm of f. Yeah, so we do need the L infinity norm of f to be small, yes, to be not too large. We need the L infinity norm of f to be not too large, otherwise it's going to affect the complexity, yes. Yes, so this is one assumption. The other hidden assumption is that we need L infinity norm of f to be not too large. That's the other hidden assumption. All right. Yeah, so let's do some examples. So let's say we have the KD graph of this group. Okay, this is the group, commutative group with these 15 elements, okay, times itself. So this is just a graph of this, except that we have to glue this one with this, okay, glue this one with this, okay. It's discrete torus. Okay, so this is the discrete torus. Take the adjacency matrix and then take this diagonal of epsilon 1 to epsilon n. So these epsilon 1 to epsilon n are IID Bernoulli plus or minus 1 random variable. So D is a random diagonal matrix. So we take expectation of this. So this type of thing that appears in this context of random Schrödinger operator, D plus A, this appears in the context of random Schrödinger operator, except that people will consider this, rather than A, they consider the Laplacian, but it's really the same except up to an identity, a multiple of identity. So yes. But for this random Schrödinger operator, this type of thing, if you want to compute this expectation directly, that's going to be hard. I mean, what's the direct way to do it? I mean, I'm not talking about using law of large number. Of course, if you use law of large number, sure, you can compute this easily, but there's some risk. If you want a rigorous bound, how do you compute this? You need to expand this one, expand this to the power 20 terms, right? Because they are not commutative, okay? D and A are not commutative. If you want to expand this, they're going to be 2 to the power 20 terms. And even if you can expand that into 2 to the power 20 terms, each of them is going to be Wood, okay? A product of a bunch of D and A, and then you take expectation of the trace. That's still not a trivial task, okay? But here we can, if you look at the Fourier coefficients are all non-negative.
Yeah, why Fourier coefficients are non-negative? Why is that true for this?
Okay, you can expand this into 2 to the power 20 terms, right? And then each term is going to be a word, okay? dA, d squared A, d a cube, and then everything is non-negative, right? All the coefficients are non-negative because all the entries of A are non-negative. All the entries of A are non-negative, so everything is non-negative here. So the Fourier coefficients are all non-negative, and then we can apply the algorithm that I propose, and then we're going to get this. Now, of course, you might not be very happy with this estimation because we're only taking p to be 100. If you want to have more accuracy, then you take p to be 1000, then I'm pretty sure it's going to be much more accurate if we take p to be 1000. But anyway, what's important here is that we are not using law of large number to get an estimation where there's some risk. This is going to be true for sure. That's a theorem, not something I'm confident is true. I mean, usually people, when people do simulation, they won't put expectation when they do simulation, okay? But this is expectation. It's a rigorous math statement. There is an expectation here. Okay. All right, so here all the epsilon 1 to epsilon n, they are plus or minus 1 Bernoulli. Okay, they're taken like uniformly from the Boolean cube. What about not from the Boolean cube? What about from, let's say, uniformly from 0, 1, 2, 3, these 4 numbers? What about this? That's still possible because we can still use Bernoulli random variables to construct random variables taken from 0, 1 to 3. You just do epsilon 1 plus half of epsilon 2. That's going to give us a uniform distribution on these 4 uniformly spaced number, and then just you just shift scale these four numbers, you will get 0, 1, 2, 3. So yeah, so it's not just restricted to plus or minus 1. You can do this kind of thing, and then you can do 0, 1, 2, 3 as well. Okay. Here I just do the KD graph of just 1, 9. Okay. Yeah, so that's what we get, because here we just take P to be 300. If we take 3000, I'm pretty sure we get more accurate estimates. Again, this is a theorem, not a statement that I'm confident is true. Okay. This is rigorous. Okay. All right, because I think in random Schrödinger operator, the D is diagonal, and then the IID random variables taken from some fixed distribution. So yeah, so in random Schrödinger operator, the theta 1 to theta n, they are taken from arbitrary distribution. Okay. Okay, finally, this self-avoiding walk. So it's not really the kind of random walk you would think of, because the R, we would think of the R to be small here. But still, I checked the literature, this is still not a trivial problem, even for R small. So think of R to be not too large, as opposed to the context of random walk in statistical physics. But even so, this is not trivial. I checked the literature. If you take an R-step random walk, so we fix a starting point, take an R-step random walk, what's the probability that it's self-avoiding? What is self-avoiding? That means so R-step, that means the R plus 1 vertices it has visited. In this R plus 1 vertices it has visited, they're all distinct. So self-avoiding, that means all the vertices that it has visited are distinct. So that's what self-avoiding means. All the vertices are distinct. Well, if we want to compute this probability, well, the easiest way is to use the law of large number to compute this probability. And then you just take a random walk and then just count how many samples are self-avoiding, and then with law of large number you can estimate this. So if we want to estimate this without risk on accuracy, there might be still some risk on complexity, but without risk on accuracy, well, you can use some kind of thing that the algorithm that I propose, yeah, we can do with error up to gamma, and that's the complexity.
Who is your function f in this case? Can you say a little bit about this?
The function f is going to be really complicated because I'm not computing this directly. How do you do this? Okay. Self-avoiding is like all the R plus 1 points it has visited distinct. I'm doing some kind of opposite. Rather than distinct, they respect some partition. So let's say the starting point is equal to the third point it has visited. And then from that, deduce the self-avoiding. So we kind of like we have to compute all the partitions. Let's say the partition is that the first and the third vertex are the same, and then the second and the fifth vertex are the same. We have to compute this probability for all the partition. Yeah, so this CR is going to be huge in R. But for each partition, that's computable. How do we do that? Well, how do we count how many walks? How many walks? That's just a to the power r, right? A to the power r would give, and then you just multiply by e of the starting point, and then multiply by 111. The a to the power r will model the walk. And then how do you model walk that follows certain partition? Well, you have to insert some random diagonal A to the power R, you have A. You insert some random diagonals in between the A. That will give us the probability that it respects certain the walk respects certain partition. Yeah, so something like this. Wait a second. A1, A cube, and then B2, and then A, and then B3, something
I
like
think
this.
we don't see. Okay, so
Right in the chat. So now D1, D2, D3, they are not the same. Just some special choice of random diagonal will produce this one.
but can you say what will be degree of this function f from knowing the degree? I mean the maximal degree of the monomial in the Fourier representation of f.
Maximum. Oh, actually, it's not too large. Something like 2R. I think it's 2R. The maximum degree is 2R. Yeah, that's the last slide. Yeah, that's it. I just finished early.
Oh, thank you very much, Mark. Thanks for the great talk. Does anybody have any questions?
Maybe it looks to me like you're trying to approximate things using empirical distribution. Is that correct? In your...
Yes, empirical distribution, but I have to certify the empirical distribution.
So in statistical applications, usually then there's a central limit theorem that comes out, like the
central limit
empirical distribution, integrate f against empirical distribution, subtract the expected value of f, and then you multiply by, if there are n samples, you multiply by root n, and you get a central limit theorem. Do you think you have that?
No, I don't get the central limit theorem. So yeah, so this one will give an estimate, but it won't accurately get the fluctuation. No, it won't get the fluctuation around the expectation.
Okay.
Actually, I have two questions. One question is, at some point you got this G111 and you want to make sure that that is small. If it is small, it means that the complexity is better, right? If G11 is small. Now G11 equals, from what I see, it equals Laplacian of f at 0.111, just by definition of the G. Now, to make sure, from the examples what you showed me, I see that these functions have very low degree. For example, in the Schrödinger case, it was of degree 20, and in the last example, you said you can compute it's 2R, right? Degree. Now, what I want to say is that there is a theorem which says that if function has degree d, then the Laplacian at 0.111 in absolute value is bounded by d squared times L infinity norm of f. This is much better if you would have just estimated by triangle inequality and put n times L infinity norm. So the claim is that G11, this whole sum at 0.111 is bounded in absolute value d squared, d is the degree of the function f, times L infinity norm of f. It's a non-trivial statement.
Yeah, but I should say, the main difficulty is not n or d squared times f of 1, 1. The main starting point is f of 1, 1 is the big part, that because n or d squared is still polynomial in n or d. The thing is, f of 1, sometimes could be exponential in n or d. That's the main difficulty. F of 1, 1. So let's take an instance. If you take a random matrix, let's say n by n random matrix, Bernoulli.
Yes.
If you take that random matrix to the power 10, let's say, and then take a trace, N or D, it doesn't really matter. But if you put 1, 1, 1 in all the entries in that random matrix, that's much bigger than if you put IID the newly, right? It's root N bigger than
Okay,
that.
so let me, okay, maybe I didn't say it in a better way. So what I want to say is that this random matrix 2 power 20 or 10, it's a function of degree 10, right? In epsilon. The claim is that G111 is bounded by 10 square times L infinity norm of F.
But the L infinity or norm of F is the bigger problem here. Sometimes that could be exponentially.
I see. Okay, so you, okay, that's it. So perhaps you want to impose different constraints on F to bound G111, right?
Yeah, so the thing is, because here I'm assuming this non-negativity in a crucial way, and then this 111 is kind of like the, you know, the main pillar of this whole Boolean structure.
Okay.
That's the main difficulty. And I don't know how to circumvent this issue. That's a problem.
So in your examples, L infinity norm F is large, right? That's what you want, what you are saying, right?
Yeah, L infinity norm of F sometimes could be even exponentially large, maybe, yes. And that's the main difficulty. And that's what affecting the complexity, because we need the P to be much bigger than G of 1, 1. And if this one is exponentially large, then that's not good. We need to pick P to be exponentially large.
Okay. Okay, thank you very much. And thanks for the talk.